All right, so the goal is an optimization algorithm. So we want it to be fast, efficient, derivative-free, global, to evaluate expensive black box, possibly non-convex, and continuous functions. So this can be almost anything. The reason I got into it was it can be used for proposed genome assemblies or parameters for an assembler or something like that. But you can apply it to anything, big CFD codes, drug trials, something like that. You have some experiment where it takes a lot of time, money, effort, something like that, to get results. And you get these results, 1D results, and there's some huge parameter space, and you want to be able to minimize the number of experiments that you have to run in order to get some optimal result, or at least the best result possible at any given time. So there's a lot of different optimization methods. Ours fits in here. It's expensive, derivative-free, global. Here's some math. I'm going to get to the figures in a second, but basically we begin by putting a Gaussian process prior on the continuous function f. So basically we model every single point as a continuous Gaussian random variable. So multiple points are multivariate Gaussians. Then we have the posterior mean and covariance. So we update the function, what we believe about the function at any given point, with some fixed covariance function. I'm not going to go into too much detail for the slides, but basically this is how it works. So at the beginning, we have no information. So this is our prior. We have some function. We assume that it's at somewhere near 0. Then there's some variance, some noise. And as we sample points, this changes. As we get more and more information, we can slowly start to learn more and more about the system. And we're trying to optimize this as we go. So we want to minimize the number of points in which we have to sample, because each one of these is expensive, as I said before. It could take days on a supercomputer, or if it's a drug trial, it could be months or something like that. And you want to get the most information at any given point. So we can evolve the system and get more and more improvement. So the idea is we want to maximize the expected improvement at every given step. So this is the best step seen so far. The difference of whatever we're going to sample next and the best we've seen so far, we want to find the highest expected, this is the improvement, we want to find the highest expected improvement. So in this example, there's a lot of unknowns here, so the expectation of the improvement was really high. I'll show that in a second. We can also do this for many different points. So this is actually the first point where it becomes, you can start parallelizing things. There's like 3 levels of parallelization in this algorithm. So this, because we're using just regular normal variables, you can find an analytic way to maximize the expected improvement, but it becomes much more difficult when you have many, many, many different variables, and it's this huge, disgusting multivariate normal that you have to integrate over. But thankfully, there's GPUs. So I'm going to do a quick plug for GPUs, especially for the 0th years. You can get really fast, you can link them together, many cores, $500, great use of your academic allowance. Get one of these, play with it. It's a lot of fun. You learn a lot. They're easy to program. You can use ACE, like Cyrus has, or CUDA and OpenCL. They're C-like. The only problem is tight memory restrictions. But for something that's trivially parallelizable, like just Monte Carlo integration, you can get 100 times speed-ups right out of the box, quick, short lines of code. So basically, back to the original thing. As we're sampling these points, we can explicitly calculate or estimate the expected improvement from sampling any number of other points in any number of dimensions. So let's say 2 dimensions. This is a 1D example, but let's say we have 2 possible experiments we can run next. So what are the best 2 points to run given the information that we have so far? So it looks like if we sample around this point, which is lower than everywhere else we think, that would be the most optimal thing to do. And so it samples near that. So I'm only sampling with one core here, but you can find the next best set in any arbitrary dimensions. And I'll show that in a second. But basically, this evolves as you go further on. And then eventually, as you're sampling one single point at a time, you can see that, oh, OK, this is the next best points to sample. It has the highest expected improvement. So if we're going to do one more drug trial, if we have like one more chance, we should do it here. And sure enough, it samples there, but it turns out it wasn't that great. So to be able to find these points without actually calculating this for every single part of the space, we want to be able to do gradient descent or something like that on this space, this expected improvement space. And we can do that by calculating stochastic gradients, a bunch of math that I'm not going to go into, and use multi-start gradient descent. So we take our expected improvement over all these different points. So this is 2 dimensions, but you can do it in arbitrary dimensions. So this is 2 dimensions of, so 2 possible experiments, but 1 dimension in the experiment, but those can both be arbitrary. And then you calculate all the gradients, and then you just perform normal gradient descent. And the really cool thing about this is it doesn't need to be sequential. So let's say I have 10 drug trials, and I'm running them, and I get results back for 5 of them. I can take that information and plug it into the equation and have it be constrained along the points that I know that I'm sampling 5 more, so I obviously don't want to sample those again. But I can continually update my estimation of this function to be able to run another 5 drug trials, or if you have some big supercomputing facility and half the cores return a result, you can immediately start using them again. You don't have to wait for all of the information to be returned. So basically, you can strain it along a certain line. So let's say I sample here, and then I want to find the next best thing. You basically just reduce the dimension, optimize on whatever variable is free, and then can run these trials much more efficiently. So it's a lot better than like a lot of times in online systems, they use A/B testing, and they basically just like give you 2 options, and then they run them both to completion or something like that. But what you could be doing is running a huge, large set of tests and be adapting things as you go and optimally use your resources at any given point. So that's really cool. And also parallel, because you can do this obviously on many different things. And then the multi-start gradient descent is also parallel. All of this goes onto the GPU. It's so great, very fast. So here's 400 cores of a GPU all doing gradient descent on this expected improvement. You can see that they find the trough. This is some pathologically difficult problem called the Brannon function. And they all find different optima, and then we free up a few more cores. They find other optima, and they slowly sample in until they get the best improvement. And so by using multiple experiments at the same time and having them return at different times and stuff like that, you can have a much higher average improvement. This is preliminary results because, like I said, it was just a side project. So these error bars are a little large, but you can see that the more experiments or the more cores you have available to you, the better it is. So this is the sequential case, which is what a lot of things are limited to now. You have to get the result that you tested before you can decide what to do next optimally. But if you are allowed to make all these estimations, then you can actually get quite a bit more improvement in wall clock time. So quick summary. I think I went pretty fast, but quick summary. It finds the next best set of points to sample instead of just the single point. It allows for the efficient use of parallel resources. You never have something sitting idle. You never have something that you're not using. It's faster than the serial or sequential methods. Very general. You can plug anything into this. It's really great. It's completely black box. It's all open source. It's in Python with PyCUDA and C. It's all up on GitHub. Another thing for the 0th years, if you're not using Git for version control or GitHub, you should totally check that out. If you get nothing else out of my talk, go check out github.com. All my code's up here, just like with Cyrus. It's all open source, and we're preparing the paper right now. So I'd like to thank everyone who helped me with everything. I did 2 practicums. They were both great. The fellowship in general has really opened up my possibilities for research and many different experiences. The Krell staff with the infinite patience and support, and my committee, the DOE CSGF, on above. And so next, I start on Monday at Yelp, and I'm looking forward to applying these algorithms and others like them for fun and profit in San Francisco. Any questions?